Okay, so last time we saw things about when things were over real numbers, so real vector space, and we discussed symmetric bilinear form and positive definite symmetric bilinear form and so on. And then towards the end, we saw Hermitian form a little bit. So today we'll discuss more about Hermitian forms, and hopefully we'll see the statement of spectral theorem today. Yeah, if not, maybe on Wednesday. But it will at least will create the background for the for this thing. Yeah, so for the spectral theorem. Yeah, so let's start with, so I'll first, so recall this standard Hermitian form just means this formula, yeah. So a standard Hermitian form on Cn is, so if you have two vectors, x and y in Cn, then this is a pairing which gives you a complex number, which is I equals 1 to n, summation xi bar yi, yeah. So x is this and y is this. Yeah, so in other words, is x star y, so to speak. Yeah, where star means you just do the you do conjugate and then transpose. Yeah, so it's not so the over real numbers is if everything is real, then x star is same as x transpose, because conjugation doesn't make it. So in some the conjugation doesn't do anything to the real number. So in some sense, this is a generalization from real to complex. Yeah? And the matrix, so I'll tell you how to write down the matrix. So it's similar to the way we do it in the bilinear form. Yeah. So remember, this is not linear in the first variable. Yeah, because it becomes conjugate. Yes, but still you can write the matrix of this form, so we'll talk about Hermitian form next, and then if you take the standard basis, then the matrix of this standard Hermitian form will be identity. So let's see the definition. Yeah. So a Hermitian form. Yeah. A Hermitian form, it's too thick. On C, on a complex vector space V is again a function from V cross V to C, such that it is linear in linear in the first variable and conjugate linear in the second variable. Yeah. Sorry, it's not linear in the first. It's linear in the second variable. Sorry, I've written. Okay, let me just fix it. Linear in the second variable. So in y it is linear if you and conjugate linear in the first variable. Okay, and xy. So what it means is, so you know what this means, yeah. So this from V to C is a linear map. That's what it means. Yeah, V linear in the second variable means this is linear. So this is what this condition 1 is same as this. Conjugate linear means it's additive, and so this means that x plus x prime, or let's say cx plus x prime y. So in one go, you can write it as c bar x comma y plus x prime. So it's conjugate linear in in the second variable. So instead of C coming out, the conjugate of C will come out. So here C is in C and XY are in B. Okay, is this okay?
Yes.
Yeah. And then X comma Y, if you switch them, then you just have to take the conjugate. Yeah, X, Y. So it's analog of symmetric. Instead of being symmetric, it is conjugate symmetric. Yeah. So that is what Hermitian form means. And now if you are given a basis B equals B1 to V1 of V, then then the matrix of this Hermitian form with respect to B is the matrix Aij, where Aij is basically the evaluation of Vi with Vj. Yeah. So you'll if you evaluate this Hermitian form at Vi comma Vj, you'll get a complex number. That complex number is Aij. Yeah. So the definition is same like in the symmetric bilinear form or in the bilinear form. You don't, I mean, to define this, you don't really need symmetric to define the matrix of a bilinear form. But for Hermitian, we are taking this as a definition. Yeah, that's automatically conjugate lineage. It's automatically X comma Y bars. Yeah. So so what happens is if this is the matrix, then like in this bilinear form, we know that the pairing is just this U. Then when you try to compute pairing, you can do it in terms of this matrix multiplication. Yeah, so you take U to be the coordinates of X with respect to B, and why is this missing? W to be the coordinates of Y with respect to B, and that is X is so if U is the coordinate of X with respect to B, that means X is basically summation Ui Bi, where U is this vector, column vector, U1 up to Un, and similarly Y is summation Wi Bi. Okay. So if you choose the coordinates, if once you fix a basis, any vector X in V will have some coordinates. Yeah, with respect to basis. That so the vector X has coordinate U and vector Y has coordinate W. Then to complete, then what this says is that this pairing, this Hermitian evaluation of the Hermitian form at X comma Y is just this thing. Yeah. So another way to write this is U star AW. Is that okay? So the proof of this, and then so this is same to bilinear form, yeah. And moreover, so in bilinear form, we saw that if we choose another basis, then the matrix changes a bit, yeah, by conjugating by something. Yeah, so similarly, moreover, if B prime is another basis and P is the change of basis matrix, change of basis matrix from B to B prime, then the matrix of this this bilinear form with respect to B prime is and say is A prime, then A prime will be this thing, yeah, P star inverse A P inverse. Okay. So depending, yeah. So if I take B prime to B, then this inverse will go away. But I've written B to B prime, so we get this inverse. Okay. Yeah. So we already so the proof of the first part is exactly the same, and for the second part I didn't give you the proof, but I said you just work. So maybe I'll give you the proof for the second part today. And together they will have the so you can apply the same idea and you get the proof for the. So basically proof of the second part is also trivial. So here also it was just evaluation, right? You evaluate both sides and you see that they agree. So you just have to express x as this thing and y as this thing in the left-hand side and use the axioms which we have to get that both the left and right-hand side are same. So similarly, so for the moreover part, so first part is same as the symmetric form case, symmetric bilinear form case rather. So bilinear form case. Yeah. So let's look at the second part, proof of the second part. So u was the coordinate of x with respect to b. Let u prime be the coordinate of x with respect to the new basis b prime. Yeah. And w prime be the coordinate of y with respect to this basis b prime. Yeah. So that means b prime is some v1 prime to vn prime. Then what it means is that x is summation ui prime times vi prime. Yeah. And so on. So u prime is the coordinate of x with respect to this new basis b prime, and w prime is the coordinate of y with respect to this new basis b prime. Then remember that p is change of basis matrix means u prime. This new vector u prime is just p times u. Yeah, that is what change of basis matrix means. So u prime is just p times u, and w prime is just p times w. Okay. So what we so then we just equate everything. So this pairing x comma y, since A is the matrix of this Hermitian form with respect to B, it is just U star A W, right? That is from the first part. Yeah. So x comma y is just u star a w, and you can also write it as u prime star a prime w prime, where a prime is the matrix of this Hermitian form with respect to the basis b prime. Yeah, and you have to show that a prime is same as this thing. Yeah. But what is this? U prime is just pu, right? So you just substitute u prime to pu, and you're putting star. Right. So if you do so here we are, so maybe there are some properties. So we'll prove these properties. Yeah. So AB, because AB star is B star A star. Okay. So because we know what AB star is, it's just conjugate and transpose. Right. So this is straightforward. But anyway, so this is because maybe I'll just write it. So the AB star is this is same as AB bar and then transpose. But taking AB bar is just A bar times B bar. So which is same as A bar, B bar, B bar whole transpose. So you conjugate is so you first multiply and then take conjugate, or first add and then take conjugate, or is same as first take conjugate and then add and multiply. Yeah, so that is how this works, and this is same as B bar transpose A bar transpose, and that is precisely B star A star. Yeah, so that proves this identity. So once you have this, so this is true for all xy. Yeah. So for all xy in V, this is true. So that tells you that this identity u star a w is equal to u star p star a prime p w is true for all vectors u and w in Cn. Yeah. So for all u and w in Cn. So if this identity holds for all u and w in Cn, so then that means that this inner matrices are same. Yeah. For instance, you can take u to be 1 0 0, even u and v to be even, then you'll get the 1/1th entry of both this inside matrix and so on. Yeah. So that tells you that this matrix A is same as P star A prime P. Yeah. And that is precisely what we wanted to prove. So so you just multiply inverses of these things on the other side. So you get that A prime is P star A P inverse. Okay, so that proves this moreover part. Yeah, is that fine?
Yes.
Yeah, makes sense, everyone?
Yes, sir.
Okay. So a matrix A is called Hermitian if A equals A star. Yeah. And this matrix is going to be Hermitian because of this condition. Yeah. XY um, is same as YX bar. Yeah. So you can check that the matrix of a Hermitian form is Hermitian. A matrix of a Hermitian form with respect to some basis. Yeah, let me just think through once. So I suppose this is okay, right? So yeah, so if you do star of this thing, that is same as, so it's 1 by 1. So that is same as taking bar, which is, yeah, so you can prove that this matrix matrix of a Hermitian form with respect to any basis is going to be a Hermitian matrix. Okay, okay, good. And moreover, some basic properties of Hermitian of doing this is called the adjoint. A star is called the adjoint. So this is what, so this identity we just saw. So we proved this. This is straightforward because this is just A plus B bar transpose, which is same as A bar transpose plus B bar transpose, which is same as A star plus B star. Yeah. And similarly the others. So this is also straightforward because you are taking you do bar and then transpose and then again bar. So two bars cancel them out and two transposes cancel them out and you get A. And this is also okay, yeah, because okay, let's see. So A star. So how do you show this? So uh, A star times. So we want to show that A star inverse is A inverse star. Yeah, so we want to show that A star times A inverse star is identity. This is what we'll have to show. Yeah, to show that A star is inverse of A star is A inverse star. Right. So let's multiply them through and show that this is identity. So this is A bar transpose times A inverse um, A inverse bar transpose. Yeah, and so if you multiply this through, so this is a inverse bar A bar transpose. Yeah, so transpose of AB is B transpose A transpose. That is what I'm using here. And this there you go. And then this is same as so multiplying first taking bar and first taking bar and multiplying is same as first multiplying and then taking bar. So it is A inverse times A bar and then transpose. But A inverse A is identity, yeah, and taking bar of identity is identity because it consists of only real numbers, and transpose is also of identity is identity. Yeah, so you get this is identity, which for this the argument is here. Okay, yeah, makes sense. So taking the inverse of the adjoint is same as first taking the inverse and then doing the adjoint. Yeah. Any questions?
So we can, instead of going back to conjugate and then transpose, we could use the second identity that we proved, right? The AB star is equal to B star A star.
Yeah, we could have done. Yeah, so we could have jumped one step. Yeah, that's true. A star, A inverse star is simply A inverse A whole star. Yeah. Yeah. So so I could have done directly here because I'm reproving basically this, yeah, in some sense. And then one step goes away. Even better. Yeah. Good. So if you use this, then this two steps becomes one step. Okay.
Yes.
Yeah. Good. So there's some basic properties of Hermitian form is also done. So now remember we also proved something like this. So if we change the basis B, if we change the basis B to so if we have a standard Hermitian form on Cn and we change the basis to B, some other basis vector. So I don't really need this. Some other basis vector of Cn. Then the matrix of the standard Hermitian form with respect to this new basis. What happened? Okay. Yeah, so something went wrong. So the matrix of the standard Hermitian form with respect to the new basis is going to be P star, where P is some non-singular. I mean, the change of basis matrix from B to I instead of I to B. Yeah, or P is some non-singular matrix. So let me just instead of putting change of basis matrix, P belongs to GL. So I don't really care which whether it's a change of basis matrix from I to B or B to I. So here you see it, you'll have to multiply by some inverse. If I mean B to B prime, it will be P star inverse, B prime to B, then this inverse will go away. Yeah, P star. Or I mean, it is conjugate of, so adjoint of some matrix, I times that matrix, or you can write it as P times I times P star. Either way is fine. So you can, or you can write it as P star P as well. So replace P star by P by P star, then it becomes P star P. Yeah. So either way, and conversely, if A is P star or P star P for some non-singular matrix P, then the Hermitian form on Cn is the standard Hermitian form with respect to some basis of Cn. Yeah, because I mean the change of because of this result which we proved. Yeah. If we do the change of basis, then the matrix changes by this formula. Yeah. So the standard Hermitian form is the standard Hermitian. If we take the standard Hermitian form with respect to standard basis, is identity. If we change the basis for some with respect to some other basis, it will be P star. Similarly, if A is P star, then and you have a Hermitian form given by this, then if you change the basis by this P inverse map, then it will be the standard Hermitian form with respect to this new basis. So that is what this says. So in other words, so A is a matrix of the standard Hermitian form with respect to some basis, if and only if A you can write it as P times P star for some non-singular matrix P. Yeah. So the upshot of these two is summarized in this last statement, third statement. Yeah, okay. So this is same as what we were doing in this symmetric bilinear form. Instead of using their result, we will use uh, this modified one for the Hermitian form. So the ideas are same. So and last class we did it very slowly, thanks to the problem with the pen. Yeah.
So, for the result that we just saw, does it need to be that V is equal to Cn, or would it hold for any complex vector space?
Which result? Standard Hermitian form is defined only for Cn. Yeah. So you can define Hermitian form on any vector space, but the standard Hermitian form makes sense only on Cn. Yeah.
Yes.
Okay.
Yes.
So this is only for standard Hermitian form. Then only you can talk about. So on a standard Hermitian form, you get this. Okay. So such matrices have a name and it's called unitary. Yeah. So a matrix P is called unitary if you can write such matrix is not unitary, but such matrices also have some name. Maybe not. Yeah, but maybe there is a name which I'm forgetting. But let's not worry about it. So I may have written it later. There's some chat, and I'm not able to click on it. Yeah. Okay. Yeah, so for this case, we are talking about V equals Cn. Yeah, then only the standard Hermitian form makes sense. Okay. So n cross n matrix P is called unitary if P times P star is identity. Yeah. So the adjoint is basically the inverse of the matrix. So this is equivalent to saying that P star and P are inverses to each other. Okay. Is that okay? Yeah. So this is unitary. This will be useful. So in some sense, so we'll talk about what is called Hermitian space and which has an orthonormal basis. And then we'll talk about linear operator and unitary operator and those things. And you'll see that unitary operator has some nice properties. So in particular, we'll prove the spectral theorem for a bunch of operators. Unitary operator will be one of them. Okay, so basically what happens is that if let's look at it this way. So what another way to think about it is if you change the basis with respect to a unitary matrix, yeah. So if the change of basis matrix is unitary, then the standard Hermitian form remains standard Hermitian, yeah, because P star is again identity. Yeah, so it's some nice thing happens. Yeah, though you're changing basis by this P, the vectors are the orthogonality of these vectors don't change. Yeah, so the unitary means that so it's like an orthogonal matrix. Yeah, it's an analog of orthogonal matrix. So if a unitary matrix has all entries real numbers, then it is orthogonal. So orthogonality doesn't change. So now so a Hermitian form is called positive definite. So symmetric form is similar to the bilinear form. It's called symmetric bilinear form. So it's called positive definite if V, the inner product of V with itself is positive for all non-zero V. Yeah. So it's so this is not just any complex number. It has to be a real number, and it should be positive real number. So a priori, it's not clear why v comma v is. Well, it is clear that I mean, if you start, so it is real is okay. Yeah. So if you think about it, this condition says that, so if you take x comma x and you interchange it as conjugate. Yeah. So x comma x is same as x comma x conjugate. So that tells you that x comma x is a real number. Yeah. No matter which Hermitian form you take. So this is saying that if you have a positive definite Hermitian form is said to be positive definite if this real number is positive for all non-zero vector v. Okay. So maybe here we can make this note. Note v comma v is a real number for all Hermitian form. And for all v, yeah. So for any v, this is always a real number. But for positive definite, we want it to be positive, yeah, for non-zero vectors. So now, like in the real case, if we have a Hermitian form on V, then like in the symmetric bilinear, when we have a symmetric bilinear form, we showed that V has an orthogonal basis. And if the symmetric bilinear form is positive definite, then we can even ensure that it has an orthonormal basis. So same thing is true here. So we have, given a Hermitian form on V, then V has an orthogonal basis. That is, there exists x1 to xn in a basis of V such that this xi xj is 0 for I different for j, I different from j. Moreover, if this is also positive definite, then we can ensure that this is an orthonormal basis. That is xi xj is delta ij, which is same as 1 if I equals j and 0 otherwise. Okay. Is that fine, everyone? So the proof of this is exactly the same as we did. So it's the longest proof, so I don't want to redo it, but it's the same, yeah? So if this form is 0, then you sort of, then the matrix is the 0 matrix. So no matter which basis you take, it will be an orthogonal basis. And if the form is non-zero, then again you find a vector such that is pairing with itself is non-zero, and then you look at the orthogonal complement of it and write v as the direct sum of this and this vector and the orthogonal basis, and then apply induction. Yeah, so that is how we proved there. So you can repeat the same proof. You'll just have to replace symmetric bilinear by Hermitian, and then positive definite remains. Yeah. So more or less the same proof goes through in this case as well. So I'll not. So maybe I'll just write. So same proof as for the symmetric bilinear form. Bilinear case. Okay. So Hermitian is just a slight generalization of from real to you go to complex numbers. That's the only difference. Yeah. So many of the ideas which you apply to symmetric bilinear goes through to Hermitian. Okay, so let's. So remember, any Hermitian form will have an orthogonal basis, and if you have a positive definite Hermitian form, then it will have an orthonormal basis. Okay. So let's see a little bit more about Hermitian matrix and so on. Yeah. So Hermitian matrices are have a lot of nice properties. So first of all, if A is so, what is a Hermitian matrix? I did tell you what is a Hermitian. Yeah, if A equals A star. Yeah. So if A equals A star, then if you think about it, the diagonal entries of A has to be real number. Yeah, because since AII, since AIJ is same as AJI bar. Yeah, so you have to do the transpose and then take the bar. Yeah, and then the matrices are same. That is what Hermitian matrix means. Yeah. So this for all ij, this has to be true, which implies AII is equal to AII bar. Yeah, which is same as saying that the diagonal entries are real numbers. Yeah, it's conjugated result. In fact, what you can show is that eigenvalues of every Hermitian matrix is a real number. Yeah. So something more is true. So let's just see a proof of this. So if you have a Hermitian matrix A, then its eigenvalues are all real numbers. Yeah. So let A be Hermitian. And let's say lambda be an eigenvalue, yeah, so it's not writing well. Lambda be an eigenvalue of A with eigenvector with an eigen, so it corresponds to some eigenvector as well with an eigenvector x. Yeah. So what? Let's just not put underscores. Yeah, it's understood. Eigenvector x. Okay. So what do we know then? If we so what we have is that ax is lambda x. Yeah, that's what we are trying to say. So x is some non-zero vector and ax is equal to lambda x. So we want to show that lambda bar is same as lambda. Yeah, so we want to say that lambda is real. So let's look at x star ax. So this is same as x star. So lambda times x star x. Yeah, that is what we'll get. But what is x star x? X star x is the length of x. Yeah, is the norm of x. So x star x is a real number, right? So now um, have to also use a star is a. Yeah. So maybe I can, okay, so we can also write x star x is also x star a star x. Yeah, because a star is same as a star is yeah, but this multiplication is same as ax whole star x. Yeah, because of that property ab whole star is b star a star. Yeah. But what is AX? AX is same as lambda x, right? So what we get is that this is lambda x whole star x. Yeah. And what is lambda x star? It's lambda bar x star. Yeah. Because lambda is just a scalar. Yeah. So you'll have to conjugate all the entries of lambda x, which is same as multiplying by the conjugate of lambda. Yeah. Times x. Lambda times x star x. Yeah, so we get that. So this 2 implies that lambda x star x is same as lambda bar x star x. But x star x is some non-zero number. Yeah. So this implies lambda equals lambda bar, since x star x is non-zero. In fact, it's a non-zero real number, but that is not very important. As long as non-zero is good enough. Yeah, so we get that all the eigenvalues are. So lambda is so which and hence belongs to us. Yeah. So we get that all the eigenvalues are real. So in particular, so corollary is that determinant and trace of Hermitian matrix. Because determinant is just the product of eigenvalues and trace is just the sum. Yeah. So determinant and trace of Hermitian matrix is are real numbers, are in R. Yeah. Okay, everyone.
Yes, sir.
Yeah. Okay. So now let P be a non-singular matrix, n cross n non-singular matrix, and it preserves the standard Hermitian form on Cn. Yeah, so this is what I was telling you about unitary matrix. So if P star P is identical, so if it preserves the standard Hermitian form on Cn, then that means the change of basis matrix does not change change the Hermitian form. Yeah, it is still given by the identity matrix. Then what it means is that P star P is identity. Yeah. So if you do the change of base, yeah. So P be a non-singular, maybe n cross n non-singular matrix, which for change of basis. Yeah. So now maybe I should write for change of basis, then it will make sense. So any change of basis matrix is non-singular. Yeah. So it preserves the standard Hermitian form, meaning the new Hermitian, the Hermitian, if you write the Hermitian form with respect to this new basis, and if it's still standard, then that happens if, in fact, if and only if P star is, if and only if P star P is identity, i.e. P is unitary. Yeah. So that is more or less definition of that is more or less this proposition, which is on this left hand side still. Yeah. Where is this? Yeah. So the change of basis leads changes from the matrix of this Hermitian form with respect to this new basis is just P star inverse A P inverse. Yeah. So if that is also identity, that means P star inverse P inverse is identity, which is same as saying P star P is identity. Yeah. So again, you use this this thing on the left, this moreover thing on the left. So in other words, this is the definition of unitary. So unitary matrices preserves this Hermitian, preserve this standard Hermitian form. I'm rewriting this. So this already I mentioned. This is a Hermitian form on V. Then V has an orthogonal basis. Moreover, if the form is positive definite, then it has an orthonormal basis. So this is this proposition. So I don't know why I have rewritten this. Yeah. So because I guess we'll use it right now, but this is the same thing as this proposition at the end. Yeah. So twice it has come. Now we define something called a Hermitian space. Yeah. So Hermitian space. So we want to get into. We don't want to work on CN. We want to work on an abstract space and then talk about linear operators between them, and talk about when such linear operators are diagonalizable and so on. Yeah. So what is a Hermitian space? Hermitian space is a complex vector space together with a positive definite Hermitian form on it. Yeah. So so as soon as you have a positive definite Hermitian form, it will give you an orthonormal basis. Yeah. So by this proposition, we know that this Hermitian space has an orthonormal basis. Yeah. So there exists V1 to Vn such that Vi Vj is going to be delta Ij. That is what these results which we have seen a proof of gives us. Okay. So now let me state before stating the Hermitian form, I'll have to define some operators. Before stating the spectral theorem, I'll have to define some operators, and then we'll state. So definition: a linear operator or a endomorphism of V, a linear operator or T on V on a Hermitian space Hermitian space so T is a linear operator on Hermitian space V. So T is a linear map from V to itself. Yeah. So is called Hermitian. So the linear operator is called a Hermitian operator. Yeah. Why it is acting this way? Hermitian operator. If if its adjoint is itself, yeah. But I haven't told you what the adjoint of this is. If yeah, so if the matrix of T with respect to an orthonormal basis of V is a Hermitian matrix. So given any basis of V, the linear operator gives you a matrix. Yeah. So instead of taking arbitrary basis, you take an orthonormal basis of V. So that makes sense because you have a positive it's a Hermitian space. So this is a positive definite Hermitian form on V. So there exists the orthonormal basis. You take any orthonormal basis, and you look at the matrix of T with respect to this this orthonormal basis, then this matrix, if this matrix is a Hermitian matrix, then you say that that this linear operator is Hermitian. Okay. So first we should also check that this is well defined, because if I take a different different orthonormal basis, then maybe take the matrix with respect to the different orthonormal basis, then maybe it may not be Hermitian. Yeah, but that can't happen, because if you do so remark maybe. So why this is well defined? So let B and B prime be orthonormal basis of Hermitian space V. Then the change of basis, what do we know about the change of basis matrix? From B to B prime is matrix P from B to B prime is, what can we say about the change of basis matrix? It's unitary, right? I mean, this Hermitian form is with respect to B is identity, with B prime also it is identity. Yeah. So the change of basis matrix will tell you that P star is again identity. Yeah. The mate is unitary. Okay, because this pairing with respect to B is the standard Hermitian form. Yeah, its orthonormal basis means this pairing with respect to B is the if you look right, the matrix of this Hermitian form with respect to B is the identity matrix. Yeah, a matrix of this with respect to B prime is also the identity matrix. So the change of basis matrix must be unitary. Yeah. P star psi. Yeah. By that property. Is this okay, everyone? Yeah, makes sense?
Yes, sir.
So P is unitary. So now if A is Hermitian, so if the linear operator, so with respect to one basis, it is, so if the matrix, now if the matrix of T with respect to with respect to B is A, then what is the then the matrix of T with respect to B prime is P inverse AP. Yeah. So change of basis, if you do, then this is what you get. Yeah, you conjugate by the change of basis matrix, right? This is the formula we learned in the beginning of the course, right? But this is same as, but P is unitary, so P inverse is just P star. Yeah, so this is P star AP. Yeah. But so A is Hermitian. So now P star. So we are assuming A is Hermitian. We want to show that this P star AP is also Hermitian. So now you do the so if A is Hermitian, Hermitian matrix. Hermitian matrix, then P star AP whole star is P star A star P. Yeah, you just I mean, P star comes here, then A star, and then P double star, so maybe let's just write P double star. Yeah, but this is same as P star. A star is same as A, and we know that P double star is same as P. Yeah, which is precisely which means that so this is also Hermitian. P star A P is also Hermitian. Okay, so this notion is being a Hermitian operator is well defined. It doesn't matter which orthonormal basis you choose from. Yeah. Similarly, you say that this is one definition. Second definition is that you say that T is unitary if the matrix of T with respect to an orthonormal basis is unitary. If the matrix of T with respect to an orthonormal basis of V is unitary. And again, if A is unitary, and then P star AP is again unitary. Yeah, because you can check that. Yeah, for P unitary matrix. Okay, so if A is unitary, then P star AP times because P star P is identity. So and A star A is identity. So you can just check. Yeah. So it does not again depend upon the choice of the orthonormal basis. Okay, so both these definitions are okay. Now, so again, this is well defined. So I'll not write down the argument, but it's the same argument. Yeah. Just check that P star A, if A is unitary, then P star AP is also unitary. So you'll have to multiply this middle guy here with this guy. And you'll see it cancels out. Okay. So there is another way to define this unitary and Hermitian. So I'll come to it, but I want to. There is enough time, so maybe I can do this, and then we'll state this Let me state the spectral theorem because I do want, I had promised you a week ago. And then I'll come to another way of looking at these operators. Yeah. So I'll define the adjoint of a linear operator, and one can define these things in terms of the adjoint operator. Yeah. So what is the spectral theorem? So let T be a Hermitian operator on a Hermitian space. So spectral theorem. So there are various versions, meaning it works for various. The first one is this. Then we'll prove this for prove it for the unitary, and in fact we'll prove it for something more general. Yeah. So first, let's prove it for the base case, which is the Hermitian linear operator, and then something called normal operator. So let T be a normal, no, not normal, Hermitian linear operator. Normal I haven't even defined. Normal is more general than Hermitian. So Hermitian operators are normal. Let T be a Hermitian Hermitian operator normal. Yeah, it is normal. Yeah, so let T be a Hermitian operator on a. Right now it was writing all right on a Hermitian space. This. And then the conclusion is there is an orthonormal basis of V consisting of eigenvectors of T, and there is an orthonormal orthonormal basis of V consisting of eigenvectors of T. Yeah. So in other words, the eigenvectors of T generate the whole of V. Yeah. So in particular, that tells you that so the matrix of T is going to be diagonalizable. Yeah. Matrix of T T with respect to any basis is diagonalizable because it is diagonalizable with respect to this. Yeah. So in particular, if you have a Hermitian, if you have a Hermitian matrix, yeah. So Cn with the standard Hermitian form is a Hermitian space. Yeah. So if you have a Hermitian matrix, then it gives you a Hermitian Hermitian operator on Cn. Yeah, because with respect to the standard basis, the matrix is that matrix. Yeah? So if you if you want to think in terms of matrices, let M be a consequence of this is that M be a Hermitian matrix, n cross n matrix. And then it's diagonalizable. In fact, what it says is that there is an orthonormal basis of Cn consisting of eigenvectors of T. So in other words, so from the so if you change it to this new orthonormal basis, the change of matrix is going to be a unitary matrix, right? Because from identity T, you are changing into another orthonormal basis. Yeah. So then there exists P, a unitary matrix such that if you do P inverse, which is same as P star. So since it's unitary, P star and P inverse is same, MP. So you use this new basis, yeah? And P star MP is diagonal. So with respect to this new, so this P star is basically the orthonormal basis here, which are eigenvectors of T. And moreover, what are the diagonal entries? What can you say about the diagonal entries of these diagonal entries in the diagonal? Something more you can say? Yeah, can you say it louder?
Real.
Real, yeah, because we are talking about Hermitian matrices, yeah. So all the eigenvalues are real. So diagonal entries are eigenvalues and is diagonal real matrix, we can say. Yeah. Real matrix. Yeah. Okay. So this I part is basically a corollary of spectral theorem. You just apply it to Cn with M, the Hermitian matrix, and then if you apply this, you get this thing. Okay. So that's the spectral theorem. So we'll see a proof. Maybe I don't know if it. Yeah. So maybe we can do the proof if time permits. Otherwise, you'll see some. But before that, maybe I'll tell you about. So maybe we'll see the proof next time. Yeah. But I wanted to talk about adjoint operator. Yeah. So if you are given an operator on a Hermitian form, so a definition or something. So let T be a linear operator on a Hermitian space V. Yeah. So Hermitian space means a finite dimensional complex vector space together with positive definite Hermitian form. Yeah, so the adjoint of T, the adjoint operator of T. So adjoint operator of T is basically what you want to do is you fix a orthonormal basis of V. You write down the matrix of T with respect to that orthonormal basis, and you just take the adjoint matrix, and that defines, in some sense, the the adjoint of T. Yeah. So let me see. How do I write it? Yeah. So maybe is defined as follows. So let's just write those things in. So let M times I over let M be the matrix. Okay, now I started writing nice. M be the matrix of T with respect to an orthonormal basis. Orthonormal basis. So we'll fix an orthonormal basis. Basis B. Yeah. So B is some orthonormal basis. Let's fix some V1 to Vn. Yeah. Then what is T star? So so I have to define the map T star from V2 itself. Yeah. So let V be in V. Yeah. Then we can write the coordinates of V with respect to V. Yeah. And X are X be the coordinates of V with respect to B, with respect to basis B. Yeah. So in other words, X is this vector, column vector x1 to xn, and summation xi vi is basically V. Yeah, that is what this means. Then what is and let y be the so if I don't want to take M, but the adjoint of M, yeah, M star X. So y is some column vector, yeah. So and now what you do, so you just so you know what T star V, define T star of V to be summation yi vi. So basically y should be the coordinate of yi vi. Okay, so T star V is summation yi vi I equals 1. In other words, the coordinates of T star V with respect to B is, so I coordinates y is in other words y is coordinates of T star. T star V is this defined this way. So T star V is that vector whose coordinate is M star X. Okay. So yeah, so I guess it is clear that T star is a linear map, yeah, because with respect to the basis B, it's given by M star, yeah. So note T star is a linear operator on V as the matrix of T star and maybe that is more appropriate, and the matrix of T star with respect to B is M star. Okay. So this is and this is easy to check, yeah. That is a linear operator. If you take V, there are two vectors V and W, then with respect to so if the coordinate of V is X and the coordinate of W is V and V prime, let's say, and coordinate of V is X and coordinate of V prime is X prime, then T star of V plus V prime is going to be you look at M star X plus X prime, and whatever you get, you'll get here. Yeah. So maybe this you check. So there is some thing to verify, but it's a straightforward verification. So maybe this is. So I'll put it as a homework. Yeah. So this show that T star is a linear operator on V, and that the matrix of T star with respect to B is M star. Okay. So this is just straightforward verification, but you write it down. Okay. So finally, yeah. So there is another way to define T star, but maybe that we can call it as a property. So let T be a linear operator on this Hermitian space V. Hermitian space. Then TVW, this pairing is same as V T star W. Okay. So you apply T to V and then pair it with W. That is same as take V and apply T star to W and then do the pairing. So this is one way to define. You could have used this to define T star as well. So TV is there and W. So you want to define T star on W T star of W to be the unique vector such that this pairing happens. And so such a vector exists, and so such a linear operator exists and is unique is another way to sort of define it. But we'll prove. So we'll take that as definition and prove it this way. So this should happen for all VW in V. Note that by our definition, so there's something which I forgot to mention. Note T double star is just T, yeah, because T star has matrix M star, yeah. So if I take the same basis and apply this again, then we'll get M back. So T double star is same as T star, is same as T. Okay. So let's see a proof of this. Proof of this fact that This. So this is basically why it is called adjoint in some sense. I mean, it's sort of so adjoint is some notion which has this kind of property. Yeah. So it's like there is something called, or maybe this was known first and then. So basically, if you move t to the other side, then you'll have to change the operator by what is called the adjoint of. Yeah. I mean, maybe in many textbook the formula is written somewhat differently. So maybe I'll write the one which is more prominent. So this is equivalent to saying that PTW, this pairing, is same as T star V W. So because T double star is same as. Okay, so what is the proof? Okay, so let x be the coordinate of so let x be the coordinate of v with respect to the basis b, and so we fix a basis, orthonormal basis of so and y the coordinate of w with respect to b, where b is an orthonormal, so that we can bring down to a matrix computation. B is an orthonormal basis of V. Yeah. Then what is okay? First, what is V comma W? Then we will talk about TV comma W. So first, what is V comma W? If X is the coordinates of this with respect to so B is an orthonormal basis with respect to orthonormal basis for this this pairing. Yeah. So the matrix of this pairing with respect to B is, what is the matrix of the pairing with respect to B? If B is orthonormal basis, is the identity matrix, right? So the point is, so if B is V1 to Vn, then it's an orthonormal basis means what? Pi Vj is delta Ij, right? So the matrix of this is just identity. So this, what will this be? What will be V comma W? Say that again. Say that loud.
Xi bar yj delta
Why is going to be X? I mean, if the matrix was some A, then it will be X X star AY. Yeah, that is what it would be. Yeah. So here the matrix is identity. So it is X star Y. Yeah. So in other words, Xi summation Xi bar Yi. Yeah. Summation. So I don't know if you said bar or not. I didn't hear. But Xi Yi summation Xi bar Yi. Right. This is what this thing is. But this is not what we want to compute. We want to compute TVW. Yeah. So what is TVW? So we would like to do all the computation with respect to basis B. Yeah. And with respect to B, the matrix of T is some M. Yeah. So before doing that, we'll have to assume we'll have to write down that the matrix of T. So let M be the matrix of T with respect to B. Then TV, the coordinate of TV with respect to B is just M times X. Yeah. Right. So what we get is that TV comma W, this pairing is just MX star, come on, Y, yeah, which is X star M star Y, right? But what is M star Y? This is precisely, so this is X star, so this is M star Y is basically the coordinate of TW with respect to T star W, yeah? So maybe instead of writing equality, let's write the statement first. Note. By definition of T star, we know that M star Y is M star Y is the coordinate of T star W with respect to B. Yeah, because the matrix of T star with respect to B is M star. Yeah, so M star Y will be the coordinate of T star W with respect to B. Hence, hence whatever, this we get that V comma T star W is this pairing is just X star M star Y. Yeah. So you'll have to look at the coordinates of V with respect to B, which is X. You do the star, and then coordinate of this with respect to B, which is M star Y, and you just multiply these two. So that which is equal to TVW. Okay, so that completes the proof that that TVW is same as VT star W. Is that okay, everyone? So a consequence of this is that T is Hermitian. If and only if. So I mean, of course, T star has to be T. So this is the tautology because I mean that's how T star is defined. But you can write it in terms of inner product as well, equivalently. So these three conditions are equivalent, which is T star is T is Hermitian, and TV is W, because our adjoint operator is unique. Yeah, TVW is V TW for all VW in T. Yeah. So TVW is same as VTW. So you don't have to put T star there. Yeah. Because if T is Hermitian, T star is same as T. So of course, forward direction is just the definition, and converse also is okay because I mean this is sort of determined. The linear operator is determined because of this positive definiteness. Yeah, and similarly, this is the first corollary. Similarly, T is unitary. So what does it mean in what should it mean in terms, I mean, if you think of it in terms of matrix, so if the linear operator with respect to some orthonormal basis is M, then unitary means that M times M star should be identity. Yeah, so that tells you that T times T and T star are inverses to each other. Yeah, so another way to say is that T star T is identity operator on V, which is equivalent to saying, so if you try to say it in, it should preserve length. Yeah. So it's now the parallel with the orthogonal is complete. So TV TW is VW for all VW in. Okay. So yeah, so maybe so forward directions of these things are straightforward. I mean, the first equivalent statement is just the definition. Yeah, and the forward directions of both is straightforward. Okay, so maybe this forward direction of one is straightforward. Forward direction of the second one has to do. So maybe let me do the forward direction of the second and we'll stop with that. The reverse direction is some non-degeneracy condition. So which maybe I'll explain next time. So proof forward direction is, so note that TV TW by what we proved is same as V T star TW. Yeah. So we can move T to the other side, which is same as, but T star T is identity because we are assuming T is unitary. Yeah. So this is same as VW. Okay. So this follows from the previous one. Okay. So the forward directions are straightforward. Next time we will do the reverse direction. So maybe that's enough for today. So any questions? Okay, so let me just